All right, we're going to take a little look today at the concept of entropy. And so, for our purposes, the main things that you're going to want to know about it are these. First of all, that you can think of it as a synonym for disorder or randomness. Okay, so when you see this word entropy, just kind of think of it as a mess. All right, we'll tighten that definition up in a little bit here. But for starters, that's a good start. And the second thing to know about it is what's called the second law of thermodynamics, so grandiose thing. And it says that in a closed system, the total entropy will increase with time. So if you let some process happen, it's going to lead to an increase in disorder or more of a mess, right? So one little caveat or something to think about is that um, disorder can decrease in one area, but there's going to be a corresponding increase elsewhere. Another way to say that is you might make a little bit of a patch of order or neatness, but that's going to be at the expense of disorder or mess that you create elsewhere, and the overall messiness will increase. So we'll talk a little bit about that, right? So far it's abstract. Let's look at something kind of specific. So something to think about is if you compare these top two scenarios. One says there's a block that's skidding across a hot surface and it comes to rest. Um, well, you see that kind of thing happen all the time. From an entropy point of view, that's fine. And the idea is that you've got this, when the block was skidding, you've got this ordered motion of all these atoms in the block, say, drifting to the right. Well, as it skids and skids and scrapes along the surface, you're going to generate wild motions and gently heat the surface. So the end result is that the block has stopped, but now you've dissipated all this energy uh, around. So you've created more of a mess. The ordered motion of the atoms in the block have become disordered motion of atoms in the floor because you've heated it, and in the air because maybe it made sound as it skidded around. And so you've created more disorder in the world by having this block skid to a stop, right? Another scenario would be there's a block sitting on a hot surface and it just starts to pick up energy from the surface and starts to skid. From an energy point of view, that's fine because yeah, energy joules can transfer from a surface into a block and become its kinetic energy. The trouble is, from an entropy point of view, the problem here is you're taking the very disordered motion of the atoms in this hot surface, and then suddenly now it's becoming ordered motion across the surface. So this would be bizarre. You're not so likely to see that, right? So similarly, let's take a look at these bottom two scenarios. One is you have a mixture of some gases, so big molecules and small molecules. And the idea here, I say, show the arrow of time. Like, which one of these two things happened first? Okay. Well, I think almost all of us would have said the one on the right happens first, and then if you leave the system alone, it drifts over this way. Well, again, there's a bit of order in the system here in that all the small molecules are on the left and all of the big ones are on the right. And so going this way is more natural, that they kind of bumble around and start to mix. It would be kind of surprising if it had gone the other way, if we started with them all mixed and they happened to land like this, right? So the idea is, and again, in a closed system, the entropy needs to increase. The atoms were sorted by type over here, so that's low entropy. It's ordered. And on the left, it's got higher entropy. It's disordered more over here. And then, so now if we look at the next one, one of these two things happened first. And again, I think, so we want to kind of show the arrow of time, which one happened first. Again, most of us would say that the system time must have kind of flowed this way, that this side was earlier in the process. Well, here we have order in the sense of spatial arrangement. The atoms wouldn't tend to order themselves spatially like this, so we probably started with them ordered and it drifted that way. So that's another way to kind of see this tendency toward disorder or toward more of a mess. So again, the second law of thermodynamics, for processes in a closed system, the disorder needs to increase. Let's look at a couple kind of subtle cases with this, because there's a couple cases that make people kind of wonder. So I want to talk about a couple processes that people really don't have a good grip on this will kind of misinterpret. And so one process is, well, a student picks up 30 dice and places all of them with the sixes upward. Right? So the dice used to be all scattered, and now they've all got sixes upward. Well, so let's look at this. So people will say, hey, that violates this because they would say, oh, wow, you've made more order. Well, let's look at this. Well, the entropy of the dice, does this violate that second law? Does it violate this? The entropy of the dice actually did decrease. They used to be all randomized, and now they're all sixes. So there is actually more order. But the issue here is the dice were not a closed system. Somebody interacted with the system, the student did. And so you have to think about, well, that student, picked them up, all right? Well, so if you consider everything, right, the student's motion that jostled the atoms in the dice, the floor, the surrounding air, ordered chemical energy that was in, say, the Doritos that the student ate, that's now been dispersed as like heat and sound in the environment. So in this whole process, we actually made kind of more of a mess in the universe. So another couple scenarios, somebody might say, well, plant growth is amazing, right? You have these atoms that you pluck from the air. Most of the mass of a plant comes from the air, actually, not from the ground. You pluck all these atoms from the air and you make this fully grown, like maple tree, this beautifully ordered system. So again, somebody would say, hey, checkmate that, you've made more order. Again, though, this is not a closed system. Does it violate the second law? Well, it doesn't because, localized, that is a localized like decrease in the entropy, like suddenly we have this fully ordered maple tree. But that plant wasn't a closed system. The sun itself is involved in the system, and the sun is creating vast amounts of disorder as it's just spewing stuff out into the world. So you can have a little pocket of order created, but the system as a whole is creating more disorder. And then same thing with you growing up. You came from a few cells and turned into the awesome machine that you are. Does that violate the second law? Again, you are a like localized decrease in entropy, but again, you're not a closed system. You eat all kinds of stuff. You excrete a lot of waste. And you actually make a lot of entropy as you kind of bumble around. So again, you kind of want to think about things as like an open or closed system. A couple other final examples that kind of look at entropy. Let's suppose you take like a hunk of metal at 50 degrees Celsius and another little smaller hunk at 100. And we're just going to put them in contact with each other, like touch this one to that one. And we want to see kind of what's a reasonable result if we stick them together and just kind of wait and see what happens. And so what I want to look at is, are these four possible results possible? Are they possible? And do they jive with kind of entropy or energy or both? So let's look at a few. So if you look at this first one, well, this one was at 50, this one's at 100. Clearly, you're not likely to see that one, okay? This one's going to violate energy unless somebody somehow held a flame under it and pumped energy into the atom. So this process is probably, you're not going to see this happen unless somebody intervened, okay? This second one is good from both an energy point of view and an entropy point of view, okay? The thing, as far as an entropy point of view, why this is good is it used to be the case that there was a little bit of order and that the kind of faster moving atoms on average were over on the right-hand side here and the slower moving ones were here on the left, the ones with less energy. So there was a little bit of a spatial sorting of the atoms where there were more high energy ones here and more kind of lower energy ones there. Well, when we put them in contact, they bumble into each other and now that's all kind of spread out. So we've lost this spatial ordering of where the energetic atoms are and where the less energetic atoms are. So that one's good from a entropy standpoint, and it's also good from an energy standpoint because energy was transferred from one to the other. Okay, this one is interesting from an energy standpoint. Is probably okay. What you would do is you'd say, well, some energy from this 50 degrees C side happened to go into the other side. Okay, so we lost some joules and it knocked it down from 50 to 49, and this one gained those joules. And it went up by a little bit more because this side's smaller. So losing 1 degree, of temperature on this side, well, you have more kind of mass there, and that might show up as a 2 degree increase over there. So from an energy standpoint, this one's probably fine. This is bad from an entropy standpoint, though. The problem here is the atoms are even more sorted now. They were sorted a little bit, and now they're even more so. Faster molecules somehow have a preference now for being on the right. And that's going to violate this tendency toward disorder. So this is exactly why you don't see heat going from cold places to hot places. It actually violates entropy, not energy. And then finally, this last one. Well, the issue here, of course, is you've got this stored internal energy if these things are at elevated temperature. So this one's going to be a violation of energy unless energy just kind of leaked away. So if like heat left, then yeah, okay, maybe you did do this if you threw this thing into the freezer. No, not into the freezer at 23, into a slightly cool room. Then yeah, this thing would eventually lose energy out to the slightly cool room, and end up all at 23C. So that one's okay from the energy point of view and entropy point of view as well, because it simply lost the scattered motion of atoms. It kind of lost that out to the room. So a couple more little points about this. A couple other little examples. If you walked in a room and you saw five dice on the ground that were all showing 1, I say, what would you think? Just laying on the ground? I don't think you'd think they just fell off the table. I think you'd think somebody put them there. They probably didn't just fall off the table and end up like that, right? It's one bit of an issue if there's only 5. Certainly if you saw like 30 of them, okay, somebody put them like that. If you saw this on the floor, I don't think you'd be too, you wouldn't really think that somebody necessarily intervened. Maybe they did just fall off the table, land like that. So most people think, oh, they probably just fell on the floor. Why really though would you think that? Why is it that you would think somebody intervened if they're like this? Well, what we want to do is, here were 5 dice and landing like this or landing like this. Really what it is if you look at when you roll 5 dice, what outcomes are likely to happen? Well, there's only one way to make a sum of 5, all ones. So there's only kind of one way to make that happen. One way to roll a sum of 5. But to get this arrangement, which happens to be a sum of 16, it turns out there's 735 ways to do that. Okay, so of the universe of possibilities with dice, this is just incredibly unlikely. Where in the grand scheme of things, there's quite a few ways to actually make a situation that kind of looks like this. So what we can do, so this in this configuration here, the system is actually in a highly ordered or a low entropy state. Now, why would we say that? Well, here is a more formal definition of entropy beyond this disordered and ordered business. What you do is you write it like this: the entropy, which is called S, is a constant times natural log of something called the number of microstates. Okay, so let's see what that is. Well, microstate would be something like rolling 5, 4, 4, 2, 1. That's a microstate. The macrostate that goes with this microstate would be rolling a 16. Okay, well, so there's 735 ways to do this. Okay, well, so if we take a look, and there's only one way to do this. Well, so if you calculate the entropy for these two states, let's just use this formula. Well, there's one way to make a 5 happen. So you'd say it's k ln of 1. So this is a 0 entropy state, right? But there's 735 ways to do this. So it would be k ln 75. Or in units of k, it would be 6.60 times k as opposed to a low entropy state of 0, right? So again, you put a bunch of dice in a box and you shake them. The system is going to tend towards these higher entropy states, right? So this is just kind of a more formal definition of entropy. And again, as you get more and more dice, it gets just to the point where it's just incredibly unlikely to say find them all the same, because you just have too many possibilities for them to be anything but all the same number, or all ones, okay? So final little thing about this, little cool history and trivia to end up with. This Boltzmann constant K that you saw, this is the fellow that developed that. So he was just a total boss. Here is his tombstone, which I found to be really cool. Here is his definition of entropy and his constant, which shows up all over physics and chemistry. So right on, hope you enjoyed. That's a little bit about entropy.